Hello and welcome to Xamarin University. My name is Adrian Stevens and I'll be your instructor today for CSC353. And this is our class that's going to look a little bit deeper into synchronization. And as the name suggests, this class is a continuation of CSC352. So if you haven't taken that class, either as a live class or watched the recorded video, I highly recommend you do so first. And of course, before we dive into the content, make sure you've downloaded the class materials from university.xamarin.com. We'll be doing some demonstrations today, but there's some excellent source code in that download package that you'll probably want to look at either while I'm doing the demos or later on for your own reference. And with that, let's begin. As I just mentioned, this class is an extension of CSC352, where we looked at the most common forms of synchronization that you use in multi-threaded .NET applications. In this class, we'll continue that discussion by examining other primitives that .NET makes available. And we'll break this down into two categories. First, we'll examine some other synchronization primitives that are available to us beyond the monitor. And then we'll look at some new thread-safe collections that were introduced with .NET 4.5. So let's start by looking at those specialized synchro APIs. Now again, remember, monitors and locks are great for ensuring that we don't access an object or a resource from multiple threads simultaneously, and often they're an excellent choice. But there are times when you may want to allow simultaneous access, or you may need a more performant solution in specific scenarios. And .NET provides several mechanisms that can be useful in those specific cases. Let's think about waiting. Managing multiple threads often means blocking until an event occurs or a resource is available, and we want to do this efficiently. And there may be times when it's safe and efficient to allow multiple threads to read a resource, but you still need to guard against simultaneous writes. Or you may wish to regulate access to a resource by allowing n number of threads, possibly to take advantage of the executing hardware while still ensuring that you're not saturating the available hardware resources. And in more complex applications, there are objects that will help start and coordinate threads, ensuring that threads don't progress until specifically triggered. So let's look at an example using monitors. It's a bit of a refresh from CSC352. Take a look at this code. We have a static method that accepts two account objects. Now imagine we're managing transfers between two bank accounts, moving money from a savings account to a checking account. Perhaps the user accidentally transferred an incorrect amount and wants to move some of the money back from checking into savings. Maybe they added an extra zero. So we could imagine the transfer method being called twice. The first time, account from is savings and account to is checking. And the second time, the accounts are reversed. If these operations were performed on separate threads simultaneously, the first thread could start executing and lock account from, which would be checking account in that instance. The second thread does the same with the savings account object. Now, both threads are waiting on the second lock, and neither are able to progress, and we end up in a deadlock situation. Obviously not ideal. So we can refactor this code and use the heavier mutex synchronization object. We call the wait1 method to acquire the lock. And then we call the release mutex to free the lock. Now mutex is similar to monitor, but it's implemented by the operating system, not .NET, and so it's actually a lot more expensive to use. Now notice in this example though, we haven't corrected the potential deadlock scenario. So we'll update our code again. Now mutex derives from WaitHandle, so it can be used with the WaitHandle static synchronization methods such as waitAll and waitAny. Now previously the issue was that we were locking one object at a time. But by using WaitHandle waitAll, both objects are grabbed at the same time. The operating system ensures that no deadlock will occur here and that this thread will own both mutexes before returning. And just a reminder, you still need to release the mutexes when you're finished accessing the data by calling release mutex. And this will correct our deadlock scenario. Now let's look at another situation. And I'm going to start with a real-world example. So we're going to think about a restroom at an airport. So multiple people can use the restroom, and they come and go, and then when it needs to be cleaned, well, the worker waits for it to be empty, and then stops all future people from coming in while it's being cleaned. Once the cleaning is complete, the worker is finished, and then it allows people back in to use the restroom. And we could use a similar strategy in our code, allowing multiple threads to read a resource, but only allowing one thread to update the data. And we could probably think of lots of scenarios. One I like to think about is maybe a complex stock trading application, something that's doing a lot of analysis on the data. So we might have multiple threads reading and analyzing the data, and we'll have one worker thread that's actually updating that stock data, perhaps in near real time. So to do this, .NET provides the ReaderWriterLockSlim class. And it's a locking mechanism object, and it's used to allow multiple threads to read a resource, but prevents more than one object from writing to it. And so when a write is attempted, it waits until all read operations are complete. Now, any new attempts to read the resource must wait until the write is complete. And once the write is finished, multiple threads can again read the resource. So let's look at some code. Now here we see we have a shared resource, possibly caching downloaded search results, or again we could think about our stock trading and analysis application. Now we have one part of our program that's responsible for retrieving data and adding it to the cache. And you see that code at the bottom. And then we have code to access the data. Now this might be accessed by multiple parts of our program on multiple threads, our get cached value. So if we have one thread doing the writing and many reading, it's a perfect scenario for using a ReaderWriterLockSlim. And so we would start by instantiating our ReaderWriterLockSlim object. Now code that reads from the resource is surrounded by calls to enter read lock and exit read lock. And this is locking and freeing the resource. Now code that writes to the resource is surrounded by calls to enter write lock and exit write lock. Now just be careful when using the ReaderWriterLockSlim. There are several older classes with similar names that are either deprecated or a lot more expensive to use. ReaderWriterLockSlim is not a lighter version, it's a more efficient version. And so you should generally prefer types that end with slim. So when would we choose a ReaderWriterLockSlim? Well, again, recall that monitor and mutex allow only a single thread to access a resource at a time. And between those two, monitor is generally more efficient because it's implemented by .NET and not the operating system. So in most multi-threaded scenarios, a monitor is sufficient, and if you don't require multiple threads to read a resource simultaneously, it's also the most performant. Now for infrequent update cases, you can try replacing it with a ReaderWriterLockSlim, and then profile the application. Check and see if performance has improved. Generally, to see a performance advantage, your code would have significantly more reads than writes, as well as a high contention for the resource. You have multiple threads trying to access the resource at the same time. Now for certain scenarios, it's going to be more efficient. For others, it might not be. And typically you're going to need to test to find out. Now let's look at another object that we can use to allow simultaneous access to a resource. Now I'll use another real-world example. You can think of a nightclub or maybe an amusement park ride. We allow a set number of people to use the resource, to ride the ride, and when they're finished, then new users are given access. And we use a semaphore to regulate access to a resource programmatically. It can allow multiple threads to access the resource, but only to a specified limit. So perhaps we have 4 requests to read a resource, but we've specified a limit of 3 with the semaphore slim. The semaphore will block one until another completes. Now notice that D has entered before C. Semaphore slim does not guarantee a first in, first out access to the resource. And we notice when one completes now, our 4th thread, our B can enter. Now to use a semaphore slim, we start by instantiating an instance, and we pass in the allowed count to the constructor. In this example, we're using 3. and then we attempt to acquire the semaphore. Again, very similar to acquiring a lock. But notice the API includes both blocking and async versions of the wait method. And using the async version allows us to continue execution in the calling method if we're not able to acquire the semaphore, i.e. we've already reached the specified limit of accessors. Now, using the synchronous version of wait means the executing thread is blocked until it's able to acquire the semaphore and continue execution. Now, the SemaphOrSlim class does not enforce thread or task identity on calls to the wait async, and release methods. It's the programmer's responsibility to ensure that calls to wait or wait async methods are appropriately paired with calls to release methods. And again, there are additional versions of the wait method that accept cancellation tokens, so you could externally cancel the wait as well. So let's take a look at the SemaphOrSlim class. Now I've opened up a copy of the cat's diner source code. This is the same code you use in CSC352. And you remember, this is our dining philosopher's problem. We've got 5 cats. Each cat wants to eat, and we have 5 forks. And each cat needs 2 forks in order to eat. So there's some very obvious contention. If every cat tries to grab the forks, it's very likely that someone's going to end up without a fork and very possibly starve. Now we solved this in 352 using monitor, and it works quite well, and all of our cats are managed to eat. But I'm hoping that we can improve the scenario here with a SemaphOrSlim. So let's start by adding a SemaphOrSlim. And in our code base, this is going to make sense to create in our dining room object. It's the level of business layer that's really steering the ship, so to speak. So in the constructor, let's create a SemaphOrSlim, and we're going to call this bowl available. This is going to control whether the cats are able to access the food, actually eat. So we'll call this var bowl avail, and we're going to make a new SemaphOrSlim. And notice there's the old semaphore as well. Slim is not less functional, it's just a bit lighter weight, it's more performant. Now, how many threads should we allow? Well, we only want a certain number of cats to eat, and we only want enough cats to eat that are able to have forks. So it makes sense to use really half of the available forks. So we'll do count and divide by 2. This was, as an integer, we'll round down with 5, so we'll have 2 cats eating at once. Now, we'd like the cat class to respect the semaphore, so we're going to pass that in. So I think our next step is to open up our cat model object. And we're going to modify the constructor to accept the semaphore. So we'll do a SemaphOrSlim here, and we'll call this bowl avail. And let's also make a class level variable. We're going to cache this off here as well. And so we'll just save this to our class level variable. And now let's go back to the dining room and pass in the SemaphOrSlim into our cats when they're being instantiated. And it says here, we're new up our cat object. We've added a 5th parameter, a SemaphOrSlim, and we'll just pass in our bowl, or really our bowl available. So perfect, we've got a semaphore. We've passed it into the appropriate places in our application. Now it's time to wait on the semaphore. So to do that, we're going to go back to our cat class. And when our cat eats, we're going to see if the bowl is available. So let's check the semaphore. And so we'll go and we're going to wait. We're going to wait until there's room for us to use the bowl, i.e. to see if there is room. Are there too many threads using the semaphore? Are there more than 2? Once there's less than 2, we'll be able to access it. So we're going to wait here, and this will pause execution on our thread until the bowl is available. And then we'll leave the rest of the code as it is, because we'll still lock the fork and use it. And then, of course, once we're done, once we've acquired both of our locks, then we can free our semaphore. So it's really just as simple as calling the release method on our SemaphOrSlim. And if we run our application again, and we'll start our cats eating, and notice now that the bytes consumed are actually a bit more balanced using the semaphore, which makes sense because there's going to be less contention on those forks now because we're managing the number of threads, the number of cats they're allowed to eat at one time. The next thing we'll talk about in this section is coordinating activities. So sometimes the synchronization required is to wait for an event to occur to coordinate two or more threads. So we could have multiple threads running simultaneously, but we don't want them to proceed until a specific event occurs, possibly another thread has completed. Now, using our stock analysis example, we could be analyzing multiple trends on multiple threads, but we need to wait for a common result from another thread before progressing. Now, before we explore the details, we need to make sure we understand some common terms that are used when discussing coordination. And the first one is wait. So threads call a wait method to block until the coordination event occurs and progress can continue. Next, we have signal, or sometimes set. Now, a thread can signal or set to tell any waiting threads that they're ready to continue. And we have reset. We can call reset to put a coordination object back into an unsignaled state. So then new threads that wait on the object will again be blocked. So keep these terms in mind as we go through the next slides. So to coordinate, we'll use a manual reset event slim object. And manual reset events allow threads to communicate with each other by signaling. Typically, this communication concerns a task which one thread must complete before other threads can proceed. And if the signals are just used to coordinate access to shared data, well, think about that. We can probably just use a lock in that scenario. Now, this manual reset event is like a gate. So when it's open, all threads are allowed to run, and when it's closed, all threads are blocked. We use set to open the gate, and reset is used to close the gate again. So when a thread begins an activity that must complete before other threads proceed, it's going to call reset to put manual reset event slim in the non-signaled state. Now this thread can be thought of as the controlling thread. And threads that wait on the manual reset event slim will block, waiting for the signal. When the controlling thread completes the activity, it calls set to signal that the waiting threads can proceed, and then all waiting threads are released. So let's explore building a blocking queue. So multiple threads can dequeue. Each will block until data is available, and then only one thread will see the data. Multiple threads can call in queue, and if the threads are waiting on data, one thread will process it. The event starts in an unsignaled state by default, and we can specify the initial state in the constructor or call the reset method to change it back to unsignaled later on, possibly again to reset it. To unblock waiting threads, we must signal the event by calling set. Then any waiters are made ready for scheduling and have the opportunity to run. Wait causes threads to block until the event is signaled, and we can optionally pass a timeout or a cancellation token to provide for cancellation if desired. And again, we see the use of reset here, causing the event to move back to the unsignaled state. Another common coordination style is to wait until a set number of activities have occurred or completed. So for example, we performed an operation n number of times, the number you would like to specify, or n units of work have finished. And then we can achieve this coordination style using a countdown event object. Now, countdown event unblocks waiting threads when it's been signaled a specific number of times. So we instantiate an instance of countdown event, and we pass in the number of times we require it to be signaled before unblocking. And in this case, we've set that to 5. Now then, each subordinate task or thread signals the countdown event when their work is complete by calling the signal method. And we can block waiting for all of the operations to occur, and this supplying an additional timeout or cancellation token. And if we need to check the state of the countdown event object, we can look at properties to determine how many operations have been counted so far. We do that by inspecting the current count property. This of course holds the number of times it's been signaled. And we can check the initial count property. That's the number of signals required. Now sometimes it's useful to know when a set of threads have hit a certain point in their processing. We could have each thread wait until all the other threads have also hit that same point. And once all the threads are in phase, we let them all continue. We use the barrier class to allow for this type of rendezvous coordination. And really this lets us coordinate our tasks where our work is done in phases and must be synchronized between these phases. So here we have 4 threads running in parallel. And threads A, B, and C complete their work within a phase, and they signal the barrier and wait. When the 4th thread completes its work, all 4 threads continue. Now note, it doesn't matter which thread signals first. It just matters that all 4 have completed. So we'll look at the code. So to use a barrier, we create an instance, and we pass in the number of signals required before our calling threads are unblocked. When a thread is finished working within a phase, it calls the signal and wait method on the barrier instance. And this blocks the calling thread, assuming we don't have enough signals yet. And in our example code, we need 3 signals. Once the barrier receives enough of those signals, all threads are released. And when you finish using a barrier, you should always dispose of it. Now, the barrier can be updated after initialization. So for example, you can add additional participants. This will increase the number of signals required before release. And additionally, the count can be lowered by using the remove participant method. Adding and removing participants will not affect threads which are not waiting on the barrier, only threads that eventually call signal and wait or are already waiting. And we can supply a phase action. And this is something we can have execute after all the threads have reached the barrier, but before the threads are released. This allows you to run some arbitrary code, something you can insert if you have any additional work that needs to be done between those phases. We covered a lot of ground in this section. We looked at using a mutex with the WaitHandle waitAll method, which in some situations will reduce the likelihood of a deadlock by allowing a single thread to acquire multiple locks in a single statement. We also examined the ReaderWriterLockSlim and SemaphoreSlim objects, and these can be used to regulate simultaneous access to a resource. And we used a barrier to coordinate thread activity into phases. Remember, these are all very useful tools in specific situations, but they're also heavier than a monitor. And if you don't have high contention for a resource, a monitor in many cases will still be the most performant option. In our next section, we'll see how to use synchronized collections. Now, recently, .NET added several new thread-safe collections. And in this section, we're going to examine how to use these new collections, and we'll see how to use one to implement a producer-consumer pattern. Now, our standard collections in .NET are not thread-safe, and they should always be synchronized in your code if they're accessed in a read-write fashion by multiple threads. And very likely, if you've needed to access a collection from multiple threads, then you've used a monitor like we see here. .NET 4.5 introduced a set of collections in the namespace System Collections Concurrent, and these collections ensure thread safety. This is done either by using locks internally or by using a lock-free thread-safe algorithm. And the first one I want to show you is concurrent queue, and this provides a first-in, first-out data collection. There's also concurrent stack, which is similar, but it provides a last-in, first-out data collection. One that should be instantly familiar is concurrent dictionary, and it works very similar to the synchronous dictionary collection. It represents a thread-safe collection of key-value pairs that, of course, can be accessed by multiple threads concurrently. And we have concurrent bag. And this provides a collection for unordered objects. And bags are really fantastic for storing objects when, of course, ordering doesn't matter, and when duplicates are allowed. And it's actually optimized for scenarios where the same thread will be both producing and consuming data within the bag. And before we jump into some code, there's something important I want to talk about. System collections current can be used within a portable class library, but it only works within specific profiles. And the reason is the namespace is not available for Windows Phone 8 Silverlight. So you must target a profile which does not include Windows Phone 8 Silverlight. And for most of our modern applications, especially using the new Xamarin Forms templates, this is not a problem. But if you have an older Xamarin Forms project or you're still supporting Windows Phone 8 Silverlight, you won't be able to use them from within a portable class library. Of course, our Xamarin targets, Windows Phone 8, Windows RT, and UWP can all be selected. Let's look at some code using concurrent collections. In this example, we're creating a concurrent queue to hold strings. Now, because multiple threads might be changing the collection, all retrieval operations are non-deterministic. They may not occur in the order requested, and they may be delayed if there's contention on the collection. But of course, there's no need to take a lock. Just try to dequeue a value. All synchronization is handled internally. In the example of a concurrent queue, if two threads call try to queue at the same time, neither operation is blocked. When a conflict is detected between the two threads, one thread will try again to retrieve the next element, and again, the synchronization is handled internally. The new collections also provide support for the producer-consumer pattern. Now, the producer-consumer pattern is a way of separating work that needs to be done from the execution of that work. It allows us to use one or more threads to produce content and add it to a collection, and then have one or more threads consume the content from the collection. The blocking collection object is a thread-safe collection class that provides an implementation of this producer-consumer pattern. And we start by instantiating a blocking collection, and you must specify the type of the collection to use as the backing storage. In this case, we're using ints. And we can perform concurrent addition and removal of items using multiple threads. And we do this using the add and take methods on our blocking collection, as you can see here. Consumers can read from the collection by calling the getConsumingEnumerable method. This method provides a consuming enumerator for the items in the collection. And then finally, when the work is complete, the producer indicates there's no additional data to be added by calling complete adding. And this will also end the enumerable loop. I've opened up another project that I'm going to use to demonstrate a blocking collection. And this is the music search project. And I have it running here on iOS. And this application will search a data collection for songs, for track lists. And we can give it some search criteria through the UI. Currently it's set to look for any song that was recorded in the year 2000 or later. And we can add additional search criteria. For example, I can pick the artist. We'll pick something popular like U2, and we'll save that. And if I search, this will give me search results. Now you may have noticed another field on the UI. This number field down here will indicate the number of threads that are going to process the search results. So currently set to 1, I can change this to 3. And now we have 3 set threads, we have 3 consumers, and it gives a time estimate. And you can play with this on various devices and see if there's any performance improvement. What you'll also notice though is that the results will come in different order depending on the number of threads you're using, and it might not even come back in the exact same order even though the backing data isn't changing. To give you a very quick tour of the project, our data is stored in a CSV file in the data folder in the portable class library. This is a Xamarin Forms application, and you can open this up and you can see we have lines representing individual songs or tracks. And you can see here that we have well over 17,000 entries, and they're broken up by name, artist, album, genre, all the bits and pieces that you're expecting to see representing a musical track. We also have a models folder, and here we have a model object, which probably does exactly what you expect it to do. It holds those pieces of data. It also has a little bit of helper code that helps it split out the lines in the CSV file. Now, I won't walk through the entire application. I'll leave some of that up to you to explore. But I want to show you the music processor class. This is really where the magic happens. This is where the blocking collection is used. And we can see that right here on line 17, we have a blocking collection that will hold tracks. That's our model object. And when we instantiate the blocking collection, remember that it's really a wrapper object. And so we pass in an instance of a concurrent queue. This is a first in, first out queue that's holding tracks. And the blocking collection will work with our queue to manage our data. We also have a predicate, and that predicate is used to evaluate the search criteria. And that predicate is passed in, and it's based on the UI settings. We won't go into the details on that, but it's interesting to look and see how that's put together if you have some time. Now notice, when we instantiate the music processor in the constructor, we pass in the number of consumers. We saw that being set in the UI. Here's the predicate being passed in. Again, this will be evaluated so we run to check our search criteria to see if we match. And then there's an action, and this action is called when a search has been found, when we have a matching track. And of course, we save off all these pieces of information in the fields above. Now to kick off the search, call the public start method in our music processor. And this is where things get interesting. Take a look at line 32. We're creating a list of tasks, and we're instantiating it and passing in one value. And notice that this task is going to call generate tracks. This is our producer, and this is going to be our producer thread. This is what's going to pull out the values from our CSV file. And then below, we're going to add several threads to consume. And notice they're going to run consume tracks. And the number of tasks that are being created here are based on the number of consumers that are passed in. Again, that's from our constructor. We pass it in, we save that off, and then we'll create a new task, or effectively a new thread in this case, to process our search results. Now let's go a little bit deeper in the code and look at our generate tracks method. Again, that's what's being called from our producer. Now generate tracks is going to come in, it's going to call read music tracks. Now read music tracks is just some basic C#, and this is just pulling out the lines of code from our CSV file. And while the thread runs, it's going to go through every line of the CSV file, and it's going to add items into our collection. Now when it's finished, notice that it calls the complete adding method. This is how we tell the collection that no more data is going to be added. And what that means is, if I have a consuming thread running, and it tries to pull data from our collection and there is no more data, then it won't block anymore. The collection will let it know that there's no more data coming and there's no reason to pause and wait for the producer to catch up. And finally, we have the consume tracks method, and this is what our consumer threads are running. And notice we're calling for each against the IEnumerable that's been returned by calling get consuming enumerable on our collection. Now this will iterate over the values in the collection, and effectively under the hood, what this is going to do is keep requesting new values from our collection. And as they're processed, they're removed from the collection. And then you see down here, it's quite simple. We pull an item out, we run the predicate. If it's true, then it matches, and we call that match action. So again, we check the predicate, and then we evaluate the action. But by doing the work on the IEnumerable, we're able to have multiple threads processing this at once, and none of the threads will ever process the same track more than once. We'll never have any repeat values or repeat comparisons. And the nature of IEnumerable takes care of that for us. And so we can have as many threads as we like processing in parallel. Let's head on over to the view models. I'm going to open up the main view model. This, of course, is the view model for our main UI. And I want to show you the onSearch method. This is called when we push our search button. Notice line 70. We're creating a concurrent bag. This is another one of our thread safe collections. And it's going to hold track view models. And these view models will be instantiated to represent each of our search results, each of our found matched tracks. So we instantiate our concurrent bag. And then here on line 73, we're instantiating our music processor, and we seal our arguments. We pass in the number of consumers, again, based on the UI. Here's our search criteria. This is our predicate. And then here's the action. This is what gets executed when we have a found result. And notice we're doing a few things here on line 75. We're newing up a track view model based on the found track, and then we're adding it to our concurrent bag, to our found tracks. And again, it makes sense that we're using a thread-safe collection because back in Music Processor, we potentially have multiple tasks, multiple threads running consume tracks, and they'll be adding results by calling the matches action on multiple threads. In this section, we introduced the new thread-safe collections available in .NET 4.5, and we saw how to use the blocking collection type to implement the producer-consumer pattern. And this brings us to the end of CSC353. Remember that you have the source code for the demo projects in the downloadable course materials. And if you have any questions, you can use the dedicated Xamarin University section of the forums to ask questions and get responses from the very talented people here at Xamarin University. If you have a deeper question, you can also schedule one-on-one time with the Xamarin University instructor. And you can do this by clicking on the office hours link in the scheduling section of the XAMU website. Thank you again for joining me here today. My name is Adrian Stevens, and I hope to see you in a live class very soon.